Hi, everybody. Hi. Thanks for coming. There's so many awesome talks going on. Thanks for your interest. I'm assuming you're here because you, like me, are interested in math education, or at the least, how could you write an algorithm that teaches people math in like a human-like way, which is what we'll be talking about today. All right, I'll just click the button. So before we dive in, I want to just take a step back and talk for a minute about how do humans think about math? Because to write an algorithm that solves math like a human would, we first have to figure out how a human would think about math. And so here's some math. I don't know about you, but when I look at this, I don't just see a bunch of characters. It's not just like a 2, and then a 0, and then a plus sign. And when you read a book, you're also not looking at individual letters. You group them together into words, and the words become like sentences, and you read them with some kind of tone. And so it's because you've learned rules about how the English language works, or other languages. And so you also have rules in your mind for how math works. And so I know that division happens before addition, and I group that together in my mind, and I know that that happens first, and 8 divided by 4 is 2, and then I can add that to 20 and get 22, and I kind of all do that without thinking at all. I just know that it's 22 because my mind has learned all these rules, and it can apply them really quickly. Here's some more math. I'm just sort of curious. I think that your mind applies more meaning to this than there is in just the characters too. Do you see the 2x as a unit? Do you see it as 2x over 3? There's no parentheses around the 2x, but you're probably still seeing it as a unit as 2x. Or maybe you see it as 2x over 3. So who sees it as the one on the left? Awesome. One on the right? Cool. So we do parse it as the one on the left, so that's good because that means it's more likely to be how you're thinking about it. Or maybe you see it as 2/3 x. And you might be wondering, nice. Yeah, anyone that wasn't either of anything that I showed? Cool. And you might be wondering why does it matter? These are all mathematically equivalent. But I think that when you show a step-by-step solution, being able to even just print it on the screen in the right way that they're thinking about it is important, but also being able to the step-by-step solution might be different. The one on the left, that's one fraction. The one on the right, that's a number times a fraction. So what you might do to show the step-by-step solution might be different. I think that if there was a space here, it might change the way you parse it. Does this change anyone's answer, maybe? Yeah, so I think that one would be the one on the right. But then they get weird questions what if it's 2 plus x thirds, a mixed fraction or something, and now this is a different math thing. And anyway, the point is, a string of math, which is the input to this algorithm we're going to be talking about, can be interpreted by our minds in lots of different ways. And thinking about how humans think about math is kind of what we're going to be getting into. So thinking about how do humans think about and solve math? How could an algorithm solve math? And can algorithms follow the same logic that a human would? What will we be talking about? All great questions. So today we're going to be talking about, I'll start by introducing myself. We'll talk about why mathsteps, which is this algorithm, why it was built and how it was built, and not just how it produces some step-by-step solution, but a step-by-step solution that can provide a good learning experience. We'll talk about some of the limitations of mathsteps because all technology has its flaws and its limitations, and we'll also talk about the future of mathsteps and things that could be done with tech to do stuff for math education. So let's get into it. My name is Evy. Hello. I am a computer science student at the University of Waterloo, and I'm really interested in education. I'm currently interning at Asana on their infrastructure team, but being a Waterloo student, I've done a whole bunch of internships, more than on this slide. And in general, I'm really interested in working on technology related to how people think about things, and I like working on technology that does social good, and that's sort of why I started working on this at one of my internships at a company called Socratic. So Socratic is an app. I worked there a year ago, and they make an app where you take a picture of your homework, It scans it, it figures out what you're asking, what subject it is, and then it provides you a bunch of like teaching resources to learn more about that topic and help you solve your homework. And when I got there, they were like just thinking about doing math stuff. So they were like, oh, it turns out like half of our queries are math, because everyone takes math, everyone takes it like every year of school, and once you like get one part that's kind of challenging, you're like screwed for the rest of your like educational career, because everything like builds on each other, and a lot of people just end up like having a lot of trouble with math. It was something that I really enjoyed. Like I was able to have like really good teachers and resources, and I really enjoy like showing my work and doing math. But a lot of people don't, and they come to the app to ask math questions, and so we wanted to provide a step-by-step solution, a good step-by-step solution. And how do we define good? It should be detailed, which means not just here's the answer, but like some steps along the way of how that happened. It should have good explanations, so like why that step happened. And it should be intuitive, because there's lots of ways to get to the answer, but some of them a human will be like, well, why did you, like that makes no sense. And some of them will be intuitive to them based off of how they learned to do it in school and stuff. And it should pretty much be like a human tutor, but like not human. And this is what it looked like in the Socratic app when I finished my internship. It scans like a picture of math, which is not part of mathsteps at all, but it's just really cool, so I want to show you. It does math OCR, then it takes that, and then it has this like step-by-step solution that you can look through. I wanted to mention that mathsteps only does algebra right now, so it's like simplifying expressions, solving equations. The Socratic app has a private fork of the code, and they added some calculus support, but that's kind of the extent, the scope of what we'll be talking about today. So you might be wondering, there's already like step-by-step math solvers out there, like, why build a new one? And the main answer is we wanted something that we could use, and all the existing ones are closed source. So we built our own, and then we made it open source so that other people can also work on it and make it good and stuff like that. It's also worth noting that like even some of the existing math solvers out there, like Wolfram Alpha, not free anymore. It was free when I was doing integrals, but now if you want an integral step-by-step solution, you have to pay like $2 a month for it or something. So, and we wanted to make sure that we were focused on teaching. So there's existing open source software out there that does stuff related to math or solving math, but doesn't necessarily show a step-by-step solution or doesn't like focus on the teaching aspect of it. And so as far as I know, mathsteps is like the first open source teaching-focused math solver, which is exciting. So at this point, you might be wondering, how did we build it? And that is what we're going to talk about next. So the input is ASCII math, just like letters and numbers and symbols that you can type out on the keyboard. That's parsed into a parse tree, and then you iterate over that tree a bunch of times, applying a bunch of different possible simplifications, and then at some point you decide that there's like no more simplifications that can be done, and then we say that we've reached the most simplified form, which again, like all these things are like kind of arbitrary, but we'll get into that. So the first part, parsing input. This is kind of what I meant by ASCII math. So you can see here, like the 2 for x squared, it's not like a little tiny 2 in the corner, like you literally it's like x caret 2. So these are like things you could type out on your keyboard. And when you look at this, you might think like, oh, I can see that that 1 plus 2 is in parentheses, and your mind kind of like groups that into a chunk. Or you see the -3, and you know that that's an argument to the absolute value function. Or you could use your knowledge of order of operations and know that the multiplication part happens before the subtraction part. How could we put this into some data structure that a computer can also apply this knowledge? A parse tree. Okay, so Math.js is this really awesome open source math library, and they have a really great parser, and it makes this tree, and it was really helpful, and Math.js is great. And so the way this works, you can see here, like the 1 plus 2 is in its like own subtree. The -3 is an argument to the absolute value function. So like all the kinds of things that you parsed in your mind was also parsed into this tree. And that becomes really helpful for the algorithm. At this point, I kind of wanted to go back to that thing I said earlier where there's existing open source math tools that are not necessarily suited for like a step-by-step solution or for something focused on teaching. And here's like a really good example. So computer algebra system is a really cool piece of technology. It like takes in math, like a string of math, and it can simplify or solve things for you and a bunch of other stuff. And me going into this project was like, oh, I'll just take this, and then I'll like look in the code and like find each step-by-step part and like take that out, because of course a computer is doing something like a human does. Nope, not at all. So I was looking at SymPy, which is like a Python computer algebra system. And when I parsed x minus y plus 2/3, it like immediately turned it into this other tree, which was x plus minus 1 times y, which is like kind of like minus y, but not, plus 2 times 3 to the minus 1. So there's no more division. There's only multiplication by the inverse. And I was like, well, this is great. Now if I want to do a step-by-step solution, I have like no idea what the user inputted originally, and like there's like no way. And I was confused at first why SymPy might do that, but honestly, like their goal is to get to the solution, and if they don't have as many operations, now they only have addition, multiplication, and exponentiation. There's no more division or subtraction, so there's less stuff for them to deal with. So it's better for their goal. And the goal of the computer algebra system is the answer. Our goal is a step-by-step solution. So even as early in like the algorithm design as just like what data structure are we going to use, we are like already going down different paths. Another thing that we came across while designing our tree was realizing that arithmetic operations are binary. And by that I mean I was like scanning 2 plus 3 plus 4, like putting that through the parser. I was expecting like one plus node with 3 children, 2, 3, and 4, but instead I got like 2 plus 3 plus 4, or 2 plus 3 plus 4. I was like, why is this tree binary? Why? That doesn't make sense to my like the way that I think about math. And turns out that's like actually the way the plus operator is defined. Like it's an addition between the left side of the plus operator and the right side of the plus operator. And that's like how it works. But because plus and also multiplication, they're both commutative and associative, so like we think of it in our minds as if it's just like an n-ary operation and it can have any number of arguments. And I was like, oh, okay, well, like maybe this binary tree will be fine. Like we'll see what happens. And then I got to something like this. And this kind of thing comes up a lot, like collecting and combining like terms. You find the 2 x's and group them together, and the 2 2's and add them together. And it was really hard with a tree that is all like spread out like that when you have a binary tree. And you have to like kind of iterate over it and figure out like what arguments are candidates for collecting, and it was not fun. And I was like, well, the way that we do it as humans is we just look at all the things that are being added together for things that are similar. And so we flattened the tree, and it was way easier. We're actually converting over to a new parser soon that my friend Kevin at Khan Academy is working on, and it will parse the tree automatically and flatten it automatically as it's parsing, which I'm excited about. So we have a tree. That's great. Now we need to do the steps. We need to simplify things step by step. Ooh, baby, gotta get to you, girl. I didn't know the song until I started my internship, and then my like intern mentor was singing it a lot, and then it was like stuck in my head for 4 months, and I just wanted to share that. Okay, so now we're simplifying things step by step. The reason that simplification is such like a big thing, this is most of what mathsteps does. There's lots of other things you can do in math, but I think at the end usually you're simplifying your answer, or a lot of like questions that students have in like early school or like middle school is around simplifying stuff. So that's what we focus on. And an example of a simplifying rule would be something like something to the 0 simplifying to 1, or taking 2 numbers and adding them together, or the 1 in the bottom right is like combining the 2x and the x to become 3x. And the way that we match a rule like this is with a tree search. So for example, the rule something to the 0 becoming 1, you can go through the tree, try to find something that's an exponent node, and then try to see whether the exponent is 0, and if both of those things are true, then you can replace that whole thing with a 1. And that's how like all of the rules work. It looks through the tree, tries to find a matching rule, and then it will like replace that with whatever the simplified version is. As a note, for those of you that are like, but what if it's 0 to the 0? That's undefined. I know, and we don't do anything about it right now. But it's on my mind. And like adding capability for like catching errors and like how that would work and what it would return and stuff is something we're exploring right now. So you're welcome to contribute to that. So that's pretty much how it works. We have some ASCII input, we parse it, we do a bunch of tree searches to try to match rules, and we simplify. So we can have a step-by-step solution now. But I don't think that that's like the most interesting part of this. I think the part that gets really neat is like not just a step-by-step solution, but a good one that has steps that are like intuitive and like teach well. And so there's like so many things that we could do to do that and lots that we haven't done yet, but I want to share some of the things that we've done so far. So one thing is the way that we structure the tree search. So we were just talking about tree searches here. Yeah, so searching through the tree, matching a rule. There are two different ways that we can do that search. One is a post-order search, which tests the parent for the rule post its children. So look at the children first. If the rule doesn't match, then you check the parent. A pre-order search will check the parent first. And that can change how the solution looks. So for the rule something to the 0 is 1, if we were using a post-order search and looking at the children first, and someone inputted something like x to the 0, which I know doesn't really make that much, like, not that many people would ask that, but it's possible. What that would simplify to is it would look deeper in the tree first, and it would match the more like inside x to the 0. So you would have x to the 0 becoming 1 to the 0, and then the next time it would become 1. But if we had a pre-order search, it could just become 1 right away, which I think makes more sense. If you have a really big expression all to the power of 0, and you can just make that 1, and algorithms often we like to take shortcuts if we can and not do extra work. In teaching, sometimes the not doing extra work thing is not great for teaching, but I think in this case it does make sense. So that search is in mathsteps as a pre-order search. But some searches are better as post-order searches. For example, like adding numbers together is only going to match at the bottom of the tree, so it may as well look at the bottom of the tree first. And that is more efficient. So some post-order, some pre-order for like algorithmic efficiency sometimes, but mostly just for like optimizing learning, like in this case. Another question I get a lot is like, how do you choose which simplification to happen first? This is like a screen video of our code, and this is like all the different rules that you can possibly match. There's like a whole bunch of them, and it's only a very small subset of existing math. And how do we pick which one happens first? Like often it's arbitrary, but there are reasons why sometimes we do certain rules first. So this is how it's structured in the code. We have this list of tree searches. Each group is a certain category of search. So the first one is basic searches. So the one that we just saw, something to the 0 is 1. May as well do that first, because if that's the whole question, then we're done. Or something like something to the times 0 is 0. Or something times 1 is itself. I guess I have to just kind of clean that up at the beginning. And that's why those searches happen first. If none of those rules can be matched anywhere in the tree, then we go on to this next one that I just like to put high up because I really don't like the way that looks, like 2 over x over 6. It's very confusing to look at, but it is legal to parse. And so someone could put that in there, and then you can just multiply by the inverse, and that kind of standardizes the way that things look so that people aren't seeing weird things that confuse them, but also the algorithm can assume that a fraction won't have a numerator or denominator that's also a fraction, because that's confusing. Another thing that we do to try to teach well is think about good teaching isn't necessarily the most simple or basic or the fewest steps. Sometimes you need to show a bit more detail. And so here We have like x times x squared becoming x cubed. And even in writing the code for this, I was like, okay, where does the 3 come from? I need to like figure out what the new exponent is. And I think it would be the same for a human that is like trying to learn this for the first time or still working on it. And the answer is you add the exponents together. But then you might be like, where did that 1 come from? There's no 1. Well, x is the same as x to the 1, and then you can add the 1 and the 2 together, and then you get 3. And that was something that I had to do in programming it, and it's also something that like a human might need to know. And so it's important to like expose those steps and show those details when it's something new to someone so that they can understand it. Pretty much just like having pedagogical goals, where pedagogy is just like a word for teaching theory. Like caring about teaching makes things more complex. So it could have more code, there could be more output, but that like creates a better learning experience. So we'll do that. However, complexity can make things more complex. And we had this technical complexity issue here where we were having these steps for adding fractions. It's like a thing that a lot of students have trouble with because there's a lot to it. The first step is to work towards having a common denominator. And you might notice that like in that process, it gets a little bit like less simplified, even though we're going towards something that's more simplified. And so at this point in mathsteps, we were just doing one step and then without any context, figuring out what the next step was. So just keeping going through, coming up with a new rule that matches. But that gets like a little weird here because 2 times 5 over 3 times 5 without any like context, you cancel out the 5s. Then you go through everything again and you're like, oh, we need to add fractions, so let's multiply by 5 on the top and the bottom. And then it goes through and it's like, oh, well, those 5s need to be canceled out. And I was like, no, what are we going to do? And then I tried moving the order of the rules around so that like the right thing would happen first before like the other thing, but like then other things broke. And I was like, how do humans know what to do? Like they just know that they're in the middle of adding fractions. So now we just group all of these steps together. We know that we're adding fractions, and then we do all of the steps in sequence, and then return them all together as substeps of the step adding fractions. And this is awesome for like so many reasons. One of them is to avoid this infinite loop situation. Another one is like we don't have to do all the work going through all those possible steps to figure out what's happening next. Like we know what's going to happen next. We're adding fractions. Like that's the next thing that happens. And it also is really nice for, this is the demo, a screenshot of it, but you can collapse those substeps. So let's say you like already know how adding fractions work and you don't want to see the details. You don't have to see the details. You can collapse them. Or maybe you want to know how it works and you can expand it. It just gives more context for what's going on, which is really great when there's a lot of steps and you don't understand that math. You can like pick and choose when to see certain details. And this is really helpful for this case too. Like I said, the bottom line was best when you don't know how this math works, but if you know that x is the same as x to the 1, having that show as a step every time can be really annoying. So having the option to show that as detail is really awesome. So now we've talked about a bunch of ways that mathsteps teaches well, but there are also a lot of ways that it could teach better, or just limitations of things it could never do. And I want to make sure that, like, in my talk, I make sure that I talk about the limitations of technology, because, like, technology isn't going to, like, make the world, like, perfect and just, like, a step-by-step solver isn't going to, like, solve all of math education. And so I want to make sure that I talk about that. So this has kind of, like, come up a couple times, like, how many steps do you show? Like, sometimes, if you show a lot of steps, people like really like that, and they like to see all the details. Sometimes, if you show like 30 steps, the student will be like, no, math is hard, that's too much, I don't like it, put it away, and they'll be scared off. Maybe they know a bunch of details of something, and you don't need to show that to them. Like, they already know how that works, and it's boring or annoying. Or maybe there's something that you don't show them that like is very key for them understanding how it works. So how many steps to show just like depends on the problem, which we do have, and the student, which we know nothing about because it's just an algorithm. Different people solve math differently. So this could be like the final solution, 8 over 5. And we can show 8 over 5 as an improper fraction. But in grade 3, I was told to leave it as a mixed fraction. In university, I was told to leave it as a decimal. So people might be looking for a specific answer, and maybe we're not giving them that answer because we have no idea what they want unless we ask, and mathstep doesn't ask right now. We also don't ask how they want to solve the question. So we might, so there's like the answer, but there's also all the steps along the way. So when I see this is like multiplying two binomials. The way that I learned to do it was you take the first term, you multiply it by all the terms on the right, and then you take the second one, you multiply it by all the terms on the right. If there was a third term, I would also multiply it by all the terms on the right. Like, I know how to like expand this to any kind of multiplying things by each other, but a lot of people learn this as FOIL. Anyone learn this as FOIL in school? Yeah, so there's the first, the outer, inner, and last, and that's how you know what the answer is, until you add a third term in either the parentheses, and then students are like, I have no idea what to do, because they don't know how the math works. It's a mnemonic. It's a way to memorize how this math works, but it's not like the why, and so they can't really like expand that. And so I tried to avoid mnemonics when in mathsteps, because I feel like it's not a good teaching tool, but also some people might get confused because different people solve math differently, and maybe they're doing homework, and at the top is like, use FOIL to answer these questions. And then they're like, am I supposed to use FOIL here? They don't mention FOIL at all. What's going on? And then like close it. So there's this like weird balance between relevant and useful to the education system, like stuff that they're learning in school, and stuff that is like relevant to like the education system as it is right now, which has its flaws. And then there's like teaching to help learning, which is like some best way of teaching where like we're really like helping people understand how it works. And there's all this research that's been done about like totally different ways to teach math, that like different fundamentals of learning, and that would be like really cool, but like would anyone use it? Would it be helpful to anyone? There's like some balance there, and so that's like really hard. But like, is there even a best way of solving something or teaching something? Like, I don't think it's objective, and so a lot of stuff that we do in mathsteps is like kind of arbitrary, or it's just at least what we think is the best. And sometimes it's just, this one seems fine. And finally, I want to make sure, and when we're talking about limitations, that a step-by-step solution isn't like a full teaching tool, right? It's just like a cool technical problem. It's not a lesson plan or like a full in-depth explanation of why. It's not going to like fix all of math education. It's just a tool that can be used like within the system. And people use it to solve their homework, which means it can be used to cheat. I don't know if any of you ever use like Wolfram Alpha or these things to like, you know, oh, I don't know how to do that integral. I like need to get some step-by-step solution that will teach me how to do it. You know, we all have done it, I think, and it is a thing that this kind of technology is used for, and so I just like keep that in mind. But there are things that we can do that can make this kind of technology better for learning, and there are things that this kind of technology could like maybe things that can be built on top of it that can also help. So lots of cool like opportunities for stuff in the future, and I'll talk about that a little bit now. So remember, we do a tree search. We know that we're adding fractions at this point. Wouldn't it be cool if, since we know you're adding fractions, we're like, hey, check out this video on Khan Academy about how to add fractions. Or even like a sub-step. Be like, hey, want to learn more about least common multiple? Here's a video about it. Because we already know this information, we're like matching these rules already. Or what if we're like, hey, you're adding fractions. This person over here is also adding fractions. And want to talk about adding fractions together? I mean, it's like silly in this example, but also teaching your peers and like talking about the problems that you're having with each other is one of the best ways to learn. And so I think it would be really cool if people could talk, if we knew that a group of people are all working on the same kind of math, to give them a place to talk about that with each other, because learning with other people is often more effective than just being by yourself copying down the answer, right? Ways to know how much detail to show. This has like come up a lot. I think there's a couple of different ways that we could do this. You could notice like when do they expand sub-steps? When are they really wanting to see more detail? Maybe we can just keep that expanded by default. Or maybe you can look at the whole question and be like, is this just a very small part of this very big problem? Then they probably don't need the details at all. But if they're just asking that particular thing, then you can show them the details. Or like you could just ask them. You could be like, hey, is this kind of thing a thing that you know? And they're like, yes. And then you can stop giving them how to do that part. And then eventually you can like get to know the learner, and you can only show them exactly the steps that are most useful to them, which is pretty much what human tutors do. And that's a lot of, I think, what is missing in something like mathsteps is getting to know the learner and being able to personalize things more. Another thing that I think would be really cool for mathsteps to do is get more context than like just a string of math, because like an equation, you can solve it, you can also graph it, you can also factor it. Which one did they ask? We don't know. We just solve the equation and hope that's what they were asking for. Or even like, what variable are they solving for? And often when people are like doing this kind of homework, they have written at the top some words that explain what the question is. So it would be great to have that context as well, because that's how humans usually solve math, not just a string. There's like instructions that go along with it. So there's more than just the string, more than just this tree. Like how can we expand this data structure to show more information? Another example of more information we might want is, let's say we have an equation like this, and we're dividing by x minus 3 on the top and the bottom. At this point, you just have x plus 5 equals 0. But some of you might be like, don't forget, x can't equal 3, because if it did, you'd be dividing by 0. I forgot this a lot in high school. This is like one of those like edge case things. But if this was the question, there would be no solution. And if you didn't remember that x can't be 3, you would be lying, which I think mathsteps does right now. So you want to be careful to like keep this extra information of what the range of certain variables can be. And there's like lots of stuff that comes up like this, things that aren't just in the expression that you want to store, because that's how humans solve math. This one's my favorite, but I feel like people would never use it, where you make them guess. This is what a human tutor can do. They sit you down and you have no choice. They're like, what do you think comes next? And you're like, I have no idea. And they're like, just guess. And you're like, okay. And that's how you learn. But I think that if this was like in some kind of app, you might be like, no, screw this. I'm going to go use Wolfram Alpha. So, you know, some balance. But definitely this is a great way to learn. And finally, machine learning. It could be cool to like train some kind of like model, take like a bunch of examples of good step-by-step solutions, whatever good means, I don't know, and then train in on that, and then you could like provide a step-by-step solution for any problem. I have no idea if this is possible or how it would be done, or if we have like enough technology for it to provide like really good step-by-step solutions, but if any of you are like interested in machine learning and have ideas about it, I would love to chat more about it, because it's like kind of neat to think about. So now we talked about all the cool things that you can do with mathsteps. You might be wondering, this is so cool. I wish I could contribute to it. And it's open source, so you can. It's written in JavaScript, all ES6. It's just like pure, like it's just an algorithm. And you can find it at that URL. We have a bunch of small tasks that should be accessible to someone that even knows like barely anything about the project, and you already know a lot about how it works now, so you're like past that point anyways. We have a bunch of really great tests. They're cool because it can just be like a string that is parsed, and then it does a bunch of steps, and then it prints it at the end. So all the tests are just like, this string becomes that string. And it's pretty much just like a step-by-step solution that you can look at and figure out how the step-by-step solutions work. So you can see how mathsteps does all of the things it does by just looking at the tests. We have a contributing document. There's lots of improvements. We like already talked about some things that mathsteps could do that you could work on, bug fixes. And even if you just want to like talk about algorithm design and writing algorithms that are optimized for teaching, I'd be down to chat about that anytime. Here are some numbers to show how popular we are. But more important than that, look where all of our contributors are from, like a cool community from around the world. If you're from any of the countries that don't have a pin on them, you should contribute so we can add a little pin. And if your country is not on this map because I cropped it, I'm sorry, especially if you're from Australia. So we have a demo that I just made like this past week, so now you can like play with it and see how it works. You can also download the Socratic app and see how that works. It's like on NPM, so you can like install it and play with it, or you can just like fork it and edit the code and do some cool stuff, and then make a pull request to contribute your cool code back. And that's it. Thanks so much for listening. If any of you want to come and talk about any of this with me, I would love to chat. I hope to see you around. Thank you.